So, welcome to lecture series on advanced linear algebra. In last lecture, I took an examples towards the end of my lectures considering matrix representation of a linear operator which is defined over the F4 cross 1, where the matrix was of the form of, if you recall, this is something like 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1 and 1, 0, 1, 0. We have seen that the characteristic polynomial is basically x square into x square minus 4 square minus 4, that f of x equal to like this thing, and we also obtained that a into a square minus 4I equal to 0. Then I told that if P denote minimal polynomial of A, then your Px is equal to x into x square minus 4. Already we have seen in the case of when an operator or matrix is diagonalizable, that its minimal polynomial is basically product of only its linear factors. So, eigenvalues are here, those are 0, 2 and minus 2. So, according to that theorem, so that Px has to be x minus 0 into x minus 2 and x plus 2. So, that are also we have seen it here, fine. Now, if I see let us quickly calculate the eigenvectors related to eigenvalue 0 and 2 and minus 2. So, eigenvector associated to eigenvalue x equal to 0, one can calculate it, that is like this. So, it will be, one has to calculate. So, a minus x equal to 0, so 0 into I, this one operating on the, say here x1, x2, x3, x4, this is equal to 0 if I go it. So, I will have a 4 equations, that is I will have basically x2 plus your x4 equal to 0 and x1 plus x3 equal to 0 and x2 plus x4 equal to 0 and x1 plus x3 equal to 0. So, this implies that I can write down that x2 is equal to minus x4 and x1 is equal to minus x3. So, there are two free variables here, x3 and x4. Let put x1 equal to x3 is equal to 1 and x4 equal to 0. So, then I will have, say V1 is a one eigenvector which is equal to x3 is equal to 1. So, x1 will be minus 1, x2 will be 0 and x1 and this is again 0 place, x4 equal to 0. So, this transpose. So, putting or considering x3 equal to 0 and x4 equal to 1, I will have V2 is equal to, so x1 will be how much? x1 minus x3, so it will be 0. So, x2 is equal to minus x4, so it is minus 1 and your x3 equal to 0, so 0 and 1. So, V1 equal to this and V2 equal to this quantity please. Similarly, let V3 denote eigenvector associated to eigenvalue 2. Then A minus 2I, I have to solve it, A minus 2I capital X equal to 0. So, this will give me, so 0 1 0 1 1 0 1 0 0 1 0 1 0 1 0, this matrix minus 2 into 1 . So, this is basically I am getting what, minus 2 1 0 1 1 minus 2 1 0 0 1 minus 2 1 1 0 1 minus 2, this one into x 1 x 2 x 3 and x 4. So, let me consider this is equal to, suppose say d x equal to 0. So, that rank of d equal to 3. So, the rank of d equal to 3, this is the homework, please, you can consider this one. Okay. And so that I will have only one free variables. So, one can have only one linearly independent eigenvector. Let V3 denote eigenvector associated to eigenvalue 2. So, already written, okay. And similarly, one can calculate V4 denote the eigenvector associated to eigenvalue say minus 2. Then I will have what? So, I will have a V1 equal to 0 into V1, a V2 equal to 0 into V2, a V3 equal to 2 into V3, a V4 equal to minus 2 into V4. So, this implies that, this implies what? I can write down say A matrix with V1, V2, V3 and V4. This is a again another matrix for V1, V2, V3, V4 a column matrix place. So, this is equal to, I can write down something like 0, 0, 2 and minus 2, this is enter 0 into again V1, V2, V3 and V4 this matrix space. So, if I denote this matrix as a P, suppose this is equal to capital P. So, we have AP equal to, suppose this is equal to, you can give suppose some capital G. So, G into P, where G is a diagonal matrix. So, this implies, and this P is invertible because each of them are linearly independent column. So, I will have multiplying P inverse from the left side, I will have P inverse AP equal to P inverse GP. I can rewrite also this is equal to P into G also, please. So, both are same, please, here. So, it will be I can write down here P into G, please. So, P inverse, so this will be, so I will have P inverse PG is equal to G matrix. So, this implies A is similar to diagonal matrix G, please. This implies A is a diagonalizable matrix, is a diagonalizable matrix also. Let me take another example. Let T and U be any two linear operators on a finite dimensional vector space, say capital V of dimension say small n. Okay, I have considered T and U be any two linear operator on a finite dimensional vector space V of dimensions this one. Here let V is equal to, for sake of simplicity, I have taken F n cross 1 matrix, so that I can give immediately matrix representation also with respect to standard order basis on F n cross 1. Let capital A and capital B are the matrix representations so here I can say this is simply F n cross 1, that will be nice. Okay. Let A and B are the matrix representation of T and U with respect to standard order basis. Order basis B equal to E1, E2 and En. Consider following problems associated to AB and BA. First, show that if lambda is an eigenvalue of AB, then it is also an eigenvalue of BA. Second, so eigenvalues are same, it does not mean that characteristic polynomial will be exactly same. So that is why let me write down again, so that characteristic polynomial of AB and BA are same. Of course, second implies 1, but 1 does not imply second please. Third, what about minimal polynomial of AB and BA? Let me answer one by one please. Let lambda be an eigenvalue of AB. Claim it is also an eigenvalue of BA. How? Since lambda is an eigenvalue of AB implies there exists, so there exists a capital X belongs to F n cross 1, I will say 0 not equal to capital X belongs to F n cross 1 such that your AB capital X equal to lambda x. So there are two possibilities, lambda may be 0 or lambda may be non-zero also. Case 1, when lambda not equal to 0 case. Lambda not equal to 0 means ABX equal to lambda x is not equal to 0, because x not equal to 0, lambda not equal to 0, so lambda x not equal to 0. Okay. We have, so if I multiply B matrix, because B is also n cross n matrix, so B into ABX will be equal to B into lambda into x is equal to lambda into B into capital X, because lambda is scalar quantity, I can take it out. So, I can write like this thing please. So, this implies lambda is an eigenvalue of BA provided Bx not equal to 0. Bx not equal to 0, since if Bx equal to 0 implies ABX equal to 0 equal to lambda into x, which is not equal to 0, which contradicts that lambda x not equal to 0. So, Bx not equal to 0. So, lambda is an eigenvalue of B A. So, if lambda is the eigenvalue of the AB, then it is also eigenvalue of B A. Now, case 2, when lambda equal to 0, when lambda equal to 0, we have AB x equal to 0 into some x for some 0 not equal to x belongs to f n cross 1. So, this implies that determinant of AB minus 0 into I equal to determinant of AB equal to 0, and determinant of AB equal to 0 implies determinant of A into determinant of B, which is equal to determinant of B into determinant of A, which is equal to determinant of B into A equal to 0. So, this implies that lambda equal to 0 is also an eigenvalue of B A. So, we have seen that if lambda is a eigenvalue of the matrix AB or operator TU, then it is also eigenvalue of UT or eigenvalue of BA please. So, what about the multiplicity of the eigenvalues in their respective characteristic polynomial? If f1 and f2 are the characteristic polynomial AB and BA, then whether the f1 will be equal to f2 or not, that is the question basically. I mean saying that what about the multiplicity of the eigenvalues in their respective polynomials means characteristic polynomial means whether characteristic polynomial of AB will be exactly equal to characteristic polynomial of BA or not, that we have to check it please. Okay. So, this one we can do using the concept of again determinant please. We have determinant of xi minus BA, this matrix I can write down, this is equal to like this determinant say I. If I consider I is the identity matrix of order n by n, then B A and x into I. If I consider this one, . Okay. So, you see this determinant of x I minus b a can be written as determinant of I a b x I multiply again I minus a 0 I. The first matrix, determinant of the first matrix is basically determinant of x I minus b a. This will basically 1, determinant of this quantity equal to 1. So, I am taking the determinant of this first type of triangular matrix will not change the original determinant of the x I minus b a please. So, without loss of generality one can write down determinant of x I minus b a equal to this quantity. Okay. But this is again if I write down simplify is basically determinant of I then minus a and plus a. Then again this here 2 1 this entry will be this row multiplied to this column. So, it will be basically again b and okay, this is equal to what a b b a, this will be minus b a and plus x into I. Okay, so, this is and this is a yeah. So, I can write like this thing please. Okay, this is simple matrix multiplication of the two matrices that is all. So, this means that I am getting what finally it is equivalent to again I can write it determinant of I 0 b and x I minus b a. Okay. So, I am getting the same thing please this one, but again the same determinant of x I minus b a can be again rewrite the determinant of I a b x I, but the second matrix I can write down minus x inverse b I 0 and I like this thing. Okay. This is equal to again use this final matrix will be I minus x inverse a b. The first entry will be I minus x inverse a b and second one will be a b and again I am getting x into x inverse and minus b again, and then this one will be 0 and x into I, is it correct? 0 x into I please. So, now determinant of this matrix please. Now, this is equal to again if you simplify then this is equal to what? Okay, this is I minus x inverse a b and this is your a and this is 0 and x into I. Okay. So, this is equal to x into I then minus x into x inverse equal to again 1. So, a into b. So, this is basically determinant of this quantity. So, this is equal to what I am getting determinant of x I minus a b. So, characteristic polynomial of b a equal to characteristic polynomial of a b. So, I am getting both of them having same characteristic polynomials. Using this simple algebra I can prove it please. But what about the minimal polynomials? Okay. So, minimal polynomial case it is not true, we can cite one examples. However, minimal polynomial of a b may differ, minimal polynomial of b a. Okay, so let me take these examples that when A equal to 0 0 1 0 and B equal to 1 0 0 0. Okay. Now, AB equal to what? 0 0 1 0 into 1 0 and 0 0. So, this is equal to 0 0 1 0. What about BA? BA equal to I am getting here 1 0 0 0 into 0 0 0. Okay. So, this is equal to 0 0 okay 0 0. So, good. So, certainly the characteristic minimal polynomial of AB and BA will be different because BA equal to 0 matrix. So, x equal to 0 is the minimal polynomial for BA, but for AB it is not true. For AB we have characteristic polynomial of AB is, so they should write f of x equal to x square. We have also characteristic polynomial of BA is also f x equal to x square, that is true, and minimal polynomial of AB certainly not x. So, minimum polynomial is not equal to x because x means AB, AB has to be 0 matrix, but AB is not a 0 matrix. However, minimal polynomial of BA is x since BA equal to 0. So, we see that here is even though both AB and BA have same characteristic polynomials, I mean same eigenvalues, but the minimal polynomial for the both the matrices are different, please. Let me consider one more nice problem, please. So, let me consider a matrix A equal to 6 minus 3 minus 2, 4 minus 1 minus 2, 10 minus 5 minus 3, or equivalent to saying that consider a linear operator T defined on F 3 cross 1 whose matrix representation is the given matrix A. Question is A similar to a diagonal matrix over R? If not, is it similar to a diagonal matrix over the complex number C? So, to answer this question, so first of all we have to find out what is the characteristic polynomials of this matrix, please. Above questions we have to first we have to find out its characteristic polynomial. So, characteristic polynomial means determinant of x I minus a, which is equal to minus 1 to the power 3, determinant of one can write down a minus x I. Okay. So, this is equal to one can write down minus 1 to the power 3 and determinants of 6 minus x minus 3 minus 2 4 minus 1 minus x minus 2 10 minus 5 minus 3 and minus x determine this quantity. So, I can write down straight away this is equal to minus 1 to the power 3 into x square plus 1 into x minus 2. We have x square plus 1 into x minus 2 is not factorizable, is able over real line R. So, this implies since we are not able to factorize over the real line, therefore, only we are getting x equal to 2. So, this implies x equal to 2 is the only eigenvalue over R, and definitely eigenspace say W2, definitely the eigenspace say W2 associated to eigenvalue 2 will have dimension 1, but check it please. As a homework. So, you will see that for x equal to 2, the dimension of the eigenspace associated to that will be 1. So, this implies that I will not have a basis, I will not have an order basis for this space your R 3 cross 1 will not get an order basis. For R 3 cross 1 as eigenvectors of given matrix A. So, this implies A is not similar to a diagonal matrix over R. The dimension of the W2 here I have asked you that to check it is basically 1. You can immediately use the results. The geometric multiplicity of an eigenvalue will never exceed the algebraic multiplicity of the corresponding eigenvalue please. Okay. Because sum of the algebraic multiplicity of the different eigenvalues of the corresponding matrix or operator will be basically the dimension of the corresponding space. So, here dimension of the space is here 3, here I am getting basically x equal to 2 and other one is basically x equal to plus minus I. So, each of them will have eigenvectors and but that will be over the complex plane. So, but over the real line only 1. So, therefore, it is not similar to this one. However, in complex plane in C, A will have 3 distinct eigenvalues I, minus I and 2, and with algebraic multiplicity as 1 each. Okay. And we know if the eigenvalues are different, then the corresponding eigenspaces are linearly independent. Okay. So, certainly one will get 3 linearly independent eigenvectors, say V1, V2, V3 associated to I minus I and 2 respectively, such that for P equal to V1, V2, V3, one will have A into P equal to V1, V2, V3 into, I can write diagonal matrix I 0 0 0 minus I 0 0 0 2. So, this is equal to P into some diagonal matrix D, please. So, this implies multiplying P inverse both sides, P inverse A P equal to D. A is similar to a diagonal matrix D. In this way, you can solve many other problems also to understand this concept, which is will be given in the assignment set, please. Hope you have understood the concept of eigenvalues and eigenvector, minimal polynomial, algebraic multiplicity, geometric multiplicity, and relation between the geometric multiplicity and algebraic multiplicities. Basically, we will use these results for our next lecture also. So, you should understand very clearly this one, please. Thank you.